Welcome back to the Deep Dive. Today, we are strapping on our virtual hard hats for a session that's pretty technically intense, but honestly absolutely vital.
We're talking about decoding industrial material failure.
Exactly. We are diving deep into the world of industrial integrity, looking at these silent structural and chemical threats.
The kind that affect pressure equipment, the pipes, the vessels, the reactors, that all have to operate under just incredible stress and high temperatures.
And we are pulling back the curtain on the fundamental physics and chemistry of how things fail. This deep dive is really your shortcut to getting well-informed on this.
It's the core knowledge, the kind you need to understand damage mechanisms, which are the very things that separate, a reliable operation from
From a catastrophic and very costly failure.
Right.
Our source material today is really targeted and incredibly potent. We're looking at a full analysis of the practice knowledge around the API-571 certification.
So this isn't just theory. We are really trying to extract the cause, the effect, the prevention, and even the appearance of 10 different ways metal can catastrophically degrade in service.
So our mission today is surgical.
To distill the most crucial nuggets of knowledge from these technical deep dives.
The idea is that you should walk away knowing not just what these failures are called, but why they happen. Why a massive steel component might just fail from the inside out.
Or thin out dramatically in one specific spot.
Okay, let's unpack this.
Yeah.
Starting with what we're calling the silent killers.
These are the structural failures that lurk deep inside the metals matrix.
Right. These are mechanisms that change the metal's properties at a molecular level, driven by chemistry, sustained stress, and heat.
And they are often completely invisible until it is far, far too late.
The first one is maybe the most insidious. High-temperature hydrogen attack, HTHA. This isn't just simple surface rust. The key insight is that the primary internal damage is caused by the formation of methane gas bubbles at grain boundaries.
That's it. That is the whole story right there. You have hydrogen gas that diffuses into carbon steel at high temperatures.
Okay.
Once it's inside, that hydrogen reacts with the carbon that's already in the steel, the very thing giving it strength, and it forms methane gas.
And this is where the structural time bomb starts ticking, because methane molecules are way bigger than the hydrogen ones they replace.
Way bigger. And suddenly they're too large to get back out of that dense metal lattice.
So they're trapped.
Precisely. It's a self-trapping mechanism.
Yeah.
This trapped high-pressure methane gas builds up along the grain boundaries, which are the weak points of the metal structure.
It's like inflating thousands of tiny, tiny balloons inside a solid block of steel.
That's a great way to put it. That intense internal pressure leads to fissuring, to decarburization, and eventually a dramatic loss of strength. It literally breaks the material from the inside out.
It's incredible how a tiny gas molecule can just undo decades of engineering just by getting stuck.
That's the danger. Now, moving from internal chemistry to structural physics, let's talk about creep damage.
Okay.
If someone asked you for a textbook definition, the best way to describe creep is as a time-dependent deformation occurring under sustained stress at high temperatures.
Time-dependent. So how is this different from, say, a sudden fracture, like from an overpressure event or something?
Well, a sudden fracture is immediate, right? It's catastrophic. It's the material's yield strength being exceeded in a moment. Creep is, well, it's the ultimate slow-motion failure.
Okay.
Imagine taking a piece of stiff, old chewing gum and hanging a tiny weight on it. It won't break right away.
Right, it'll just sit there.
But over weeks, that gum will gradually, slowly stretch and deform under that constant load. That's creep.
It's progressive damage that just accumulates over time.
Yes. And it happens when metals are stressed at temperatures typically above, say, 40% of their absolute melting point. Over years, this movement leads to the slow formation of microscopic voids and then eventual rupture.
You can't fix it.
That's the critical part. Our sources emphasize this. Once creep damage has progressed, you can't reverse it. No standard heat treatment will heal it. The clock has simply run out.
Speaking of material aging from heat, let's talk about spheroidization. It's another temperature-driven change in the microstructure.
And it's often paired with creep risk, you're right. So what's happening here is that when you expose carbon steel to prolonged high-temperature service, its internal structure starts to change.
How so?
Specifically, the strong plate-like structures, we call them lamellar carbides, they begin to transform into softer, more rounded carbide particles.
So the structure is losing its sharp load-bearing architecture.
Exactly. Think of the lamellar structure, like strong sheets reinforcing the metal. Spheroidization is like dissolving those sheets and letting them clump into little softballs.
So what's the result?
The immediate result is a reduction in tensile strength and an increase in ductility.
Now, increased ductility might sound good, but in this context, it's a bad sign. It means the steel is getting weaker, softer.
It's degrading its core capability. It's basically aging out of service, even if the surface looks perfectly fine.
Okay, so now let's combine stress and chemistry. Our final structural mechanism is amine stress corrosion cracking, or amine SCC.
Right. This is failure driven by residual tensile stresses, especially in weld areas when they're exposed to onimine solutions.
This one is a huge problem, but the prevention method is, well, it's absolutely critical. The most effective method is performing post-weld heat treatment, or PWHT, on all weldments.
Which brings up the key question. Why is that the best answer? Why not just say reduce the amine concentration or something?
It's all about the stress, isn't it?
It's all about stress relief. When you weld metal, you introduce massive localized heat. As it cools, it shrinks unevenly. This locks in residual tensile stresses.
Internal forces that are just constantly pulling the metal apart.
Exactly. Think of it like squeezing a giant spring and then locking it in that compressed state. PWHT is a controlled heating and slow cooling cycle that lets the metal lattice just relax.
It's like slowly warming that spring up until the locked-in stresses just melt away.
Precisely. And by removing that critical stress component, you eliminate the main driving force for the crack to even start, even if the corrosive amine is still there.
We talked about eliminating internal stress with PWHT. But what if stress isn't the main problem? Here's where it gets really interesting.
Ah, yes. Moving from internal integrity to how flow and specific chemicals can literally chew away at the surface.
Let's start with sulfidation corrosion.
Yeah.
This is common in refinery units that process sulfur-containing fluids at high heat.
Right. And in carbon steel systems, the corrosion rate isn't dependent on chromium, which is what you might expect.
No, it's a real dark horse element here. For carbon steel, sulfidation rates are strongly affected by the content of silicon.
Silicon.
Why silicon? You almost never hear about it being more important than chromium for high-temperature corrosion.
That's because in your standard carbon steel, there just isn't enough chromium to form a truly protective layer. So silicon steps in. It helps form a more compact and protective iron sulfide scale.
So the scale itself is the shield.
It's the shield, and silicon makes it a better shield, reducing the rate of metal loss. In these low alloy environments, silicon content is the #1 thing to look at.
Now, for a different kind of acid, naphthenic acid corrosion, or NAC. This is driven by organic acids in crude oil. For an inspector in the field, what's the telltale visual sign?
Okay, so NAC happens when you're processing high-acid crude oils at high temperatures, and the damage is very distinct. It is most commonly identified by sharp-edged pits or streamlined grooves in high-velocity areas.
The streamlined grooves, that's the key, right?
Absolutely. That appearance, the sharp pits in the grooves, it confirms that fluid velocity and turbulence are central to the attack.
So the acid attacks and the flow sweeps away any protection.
Exactly. It sweeps away any weak protective layers that try to form. So NAC is always worst in areas of high turbulence elbows, pump impellers, downstream of fittings.
That concept leads perfectly into our next one, erosion corrosion, which is really the definition of a 1-2 punch.
Mechanical wear combining disastrously with chemistry.
So where in a system are we most likely to find this?
You'll find it where the fluid path changes dramatically. So pipe, bends, elbows, and areas downstream of control valves.
And why those specific spots?
It's because the high velocity and the flow disturbances, they physically disrupt and remove the thin, passive surface films the metal relies on for protection.
They're scraping off the armor.
You are. And once that film is physically scraped away, the naked metal underneath is immediately exposed to the corrosive fluid. The chemical reaction just accelerates dramatically. It's a vicious cycle.
Okay, this next one has a truly terrifying timing factor. Polythionic acid stress corrosion cracking, PKSCC.
Ah, yes.
When does this cracking typically happen? You'd think it would be when the unit is running hot and hard, but no.
Yeah.
It typically occurs during unit shutdowns when equipment is open to air.
And if we connect this to the bigger picture, that timing is absolutely crucial for safety and maintenance planning.
So what's happened?
This failure affects what we call sensitized austenitic stainless steels. Basically steel that's been damaged by high heat exposure, which depletes the chromium at the green boundaries.
So the material is already vulnerable, but why does the failure wait until the unit stops?
Sulfur compounds build up on the surface during operation,
Yeah.
but it's only when that sulfur-containing scale reacts with oxygen and moisture from the air
During the shutdown.
during the shutdown that these highly corrosive polythionic acids are formed.
So the acid isn't even there during operation. It's created during the cool down process.
Precisely. And that acid then aggressively attacks those chromium-depleted grain boundaries. It's why inspection crews have to be so aware of PSCC risk when they open up these systems.
All right, let's shift our focus completely now. Let's talk about external factors, things happening on the outside of the pipe.
And these are often hidden from sight, which makes them extremely dangerous.
Let's start with the classic one, corrosion under insulation, or CUI.
Notoriously difficult to detect.
We know you need moisture, but temperature is the accelerator. What's the most aggressive temperature range for CUI? It's between 10 and 350 degrees Fahrenheit.
That's a huge range.
It is. So why is that specific range the corrosion Goldilocks zone?
Well, below freezing, corrosion pretty much stops. Not enough liquid water. At very high temperatures, say above 350 Fahrenheit, any water that gets in just flashes off as steam.
So the water can't stick around.
Right. But that 10 to 350 range is the sweet spot. It allows liquid water from rain, leaks, condensation to stay present for long periods of time while still providing enough thermal energy to constantly accelerate the corrosion.
And it's hidden under the insulation.
Hidden the whole time. It often goes undetected until you have catastrophic wall thinning.
Okay, finally, let's touch on general atmospheric corrosion. We know moisture and temperature matter, but what's the one airborne contaminant that just supercharges the corrosion rate?
While pollution is a factor, our sources confirm that the presence of chlorides from marine environments or cooling tower drift is the #1 accelerant.
And the mechanism there is all about breaking down that protective film, isn't it?
It is. Steel naturally forms a thin, protective oxide film. Chlorides are incredibly efficient at promoting electrochemical reactions that just break that film down and prevent it from reforming.
It's why things rust so fast near the ocean.
Or right next to a cooling tower, which is constantly spraying chloride-rich water vapor into the air.
Yeah.
Those are incredibly aggressive environments.
Wow. So what does this all mean?
Well, we spend a good bit of time on two specific types of high-temperature material aging, right? Creep and spheroidization.
Right.
And both of them gradually and irreversibly reduce the mechanical strength of the material over time. Crucially, this degradation of the internal microstructure can go on for decades without any obvious signs on the surface.
The visible metallurgical clock ticking away.
Exactly. So given that, a really critical question arises for every asset owner. How should engineers balance the initial cost savings you get from using, say, a lower grade material versus the vastly increased inspection costs that you'll need to monitor that invisible degradation over the full life cycle of the equipment?
More frequent, more complex, more invasive scans.
It's a massive financial and safety calculation. And it's a calculation that knowledge of these mechanisms forces you to confront.